So now let's summarize the desirable features of solar cells. One thing that you want to do is you want to absorb as much of the solar spectrum as possible. And how do we do that? Well, we talked about that, so we can use materials with different band gaps to try to cover the solar spectrum. That involves multi-junction or heterojunction types of structures. You also want to use materials with a high absorption coefficient in those wavelengths that make up the solar spectrum. Something else that you want to do is you want to make your solar cell as thin as possible while still satisfying that first requirement where we're absorbing as much of the solar spectrum as possible. Why do we want to make them as thin as possible? Well, that reduces the chance of recombination. You want the electron hole pairs to be generated in the depletion region or very close to the depletion region, and then after they're generated they actually make it outside of the semiconductor material into the load resistance that you're attaching the solar cell to. So you don't want, once you generate the electron hole pairs, you don't want them to recombine before they get out of the p-n junction, which means you want to reduce the amount of material making your solar cell as thin as possible to reduce the likelihood that those generated electron hole pairs are going to recombine while they're still in the semiconductor. Related to that, your recombination will be reduced if your material has a long diffusion length. So that is something that's also desirable. And in order to make the solar cell as thin as possible while still absorbing as much of the solar spectrum as possible, that also is achieved by using materials with a high absorption coefficient. So that point in number one still applies to the second goal that we have. The third thing that we can do, it's actually two things, but I'm just lumping it in to this one bullet, is to reduce reflections any place in the solar cell or even at the surface of the solar cell, because if photons are reflected, they're not getting into the p-n junction to make these electron hole pairs. So we want to reduce reflections as much as possible, and we want to keep the surface of the solar cell as clean as possible so that none of the photons are absorbed by, say, dirt on the surface, and all of the photons that are incident on our solar cell actually make it into the solar cell and generate electron hole pairs. So how do we do that? There's a couple of things that you can do, which includes putting anti-reflective coatings at any interface in your solar cell, as well as making self-cleaning surfaces at the surface of the solar cell. Another thing that we want to do is to efficiently collect our charge carriers. What does that mean? We want the metal contacts at the solar cell connecting it to the external circuit to have a very low resistance and also not block any light from getting into the solar cell. Finally, this is an economic driver, not a technical, well, it is, I guess, sort of related to technical things, but that we want the solar cells to be very low cost so that it's competitive with other energy sources. So this has to do with materials costs, which does relate to technical issues, fabrication costs, also related to the technical design of the solar cell, and how much does it cost to operate a solar cell, cost per kilowatt hour. We want that to be as low as possible. So far, we don't have a solar cell that does a very good job at all of these things at once. So there's still room for improvement, but it is something that is challenging.